I don't know if I can answer your last question, but at least I'm going to explain you what is the story about Wendelstein 7X, about the machine we have built in Greifswald and we are continue to build. Our institution has two sites, Garching and Greifswald, and we are operating at both sites big machines, big fusion research machines, and that's my story actually. But I start now with the story. What's the background? The background is the global energy consumption, and I just want to underline that the energy problem is a global one. And this is actually an interesting chart. So here we have different color codes. So from low income level to high income level. So here these three different colors, and very obviously here in Europe we are, and USA and Japan and South Korea, we have the high income levels. Also here in Australia, and also color coded is the population density. So the light color is high population density. The darker version of the color is a low population density. And this only tells you, or this chart quickly tells you, that a lot of people are living in areas of the world in lower middle, upper middle, and especially lower income levels. And since energy consumption correlates directly with the income level, the message is things are to come. And the energy consumption of the world will increase dramatically. And there are several different studies. You can try to study that in codes, in simulation codes, global simulation codes. And these are the names of these codes, so published in this paper. And then the predictions until the year 2100 are compared between these different codes. And without going into the detail, we get a certain uncertainty between the predictions, but in any case, we get a big increase of the global energy consumption, at least by a factor of 2 in the most conservative estimates, up to a factor of 4. And so the famous energy turnaround, the Energiewende, we are exercising here in Germany, is not only about changing totally the concept of energy supply, putting much more emphasis on renewables, thinking a lot about energy storage and related areas, but it's also about the need of much more energy. And that's part 2 of the story. And this is about to come. So continuously, it will starts now, and it will continuously increase the need for energy. So there are 2 things you can do there, so among all the other known primary energy sources, of course. Fission and fusion, just to make clear, so what is the difference? Fission is to split heavy nuclei into smaller ones. Fusion is to fuse small nuclei, light nuclei, to heavier ones. Okay. The principle is the same, and so Einstein's famous formula E equals mc squared, so mass and energy is the same, with a proportionality constant. And so the difference in the mass of the reaction products here gives you the energy, and the energy is released in motion. So you're creating motion, just particles are getting speed, and motion is just another word for heat, and so you're generating heat. So that's this common principle, but there are 2 different lines, fusion and fission. Now, fusion is very much in use in the universe, of course. So fusion is just the powerhouse of the universe, and our star, so our private star, the Sun, a G2 star, is just an ordinary standard star, is following the following path. That's PP fusion, so the fusion of protons, of light protons, and that's the chain that is followed. So you start with two protons, and then you generate deuterium and a positron and a neutron, and then you have a deuterium, which again collides with a proton, and then you generate helium-3, and when eventually 2 helium-3 nuclei collide, they generate helium-4, and again 2 protons. So that's the principle. Okay, great. So what is the essence? You start with protons, you end with helium-4, and again with protons, and that's why it is called a cycle. You need conditions for that, to have this process efficiently running, and the Sun is, of course, designed to match these conditions, and the conditions are summarized here. So the density of the Sun in the core is about 1,000 times the density of solids on Earth, and so it's dense. And the Sun is hot, 15 million degrees centigrade in the center, ion temperature, and the density and the temperature combine to a pretty high pressure, 10 to the 11 bar pressure, which is, of course, quite a high value. And the confinement is just done by the gravitation. Just the fact that the sun has 330,000 times the mass of the Earth produces enough gravitation to keep the plasma together. That's impossible on Earth. And so sometimes you might have read, bringing the sun on the Earth, that's of course nonsense. Scientifically, that's nonsense. It's a nice headline, but this is definitely not possible, at least not in the steady-state conditions. You can do so. You can create matter conditions like that for a nanosecond or so, with very strong lasers, for instance, or very strong beams. Really, as a continuously running system like the sun, this is impossible. But there's a replacement for that. There's an alternative fusion process, and that consists of two isotopes of hydrogen, so deuterium, so that's heavy nitrogen, and tritium, super heavy nitrogen. And if you start with both of them at a kinetic energy of about 10 kilo electron volts, so that's just the measure for the kinetic energy here expressed in electron volts. And if you make them collide with a sufficiently high probability, you are getting a fusion collision. And the fusion collision has the property that after the collision you have new products, so a neutron and a helium, and you gain a lot of energy. So here we have 14.1 MeV and 3.5 MeV. So that means we have something like an acceleration due to the fusion collision. So a fusion collision accelerates the particles, roughly speaking, by about a factor of 1,000. And so that's a nice collision. So you collide two particles, you get something new, and especially you get a lot of speed. And that's a principle, so very simply speaking, but you need a lot of them. So if you want to build a reasonable power station on Earth, say about 1 gigawatt electric power, then you need 10 to the 18 fusion processes per second and cubic meter. And that's the message, that's one of the take-home messages. To make fusion is easy. Fusion works. I'm often asked, does fusion work? Yes. So that's a very simple nuclear process which is well understood. All the cross-sections are well understood. The big exercise is to make a lot of fusion per second and cubic meter. 10 to the 18 per second and cubic meter, and that's why I'm a plasma physicist, because I have some ideas of many particles, of many particles sitting together, which is the matter of state called plasma. Here we go. The efficiency of this fuel is quite impressive. So again, so some simple figures. You can compare 1 gram of deuterium-tritium fuel mixture with 1 gram of coal, and there's a factor of 10 million. So 1 gram mixture of deuterium-tritium yields the same energy as 10 million gram of coal burned just by chemical burning. And so it's a very efficient fuel, and that makes it so attractive. Is it available? Yes, kind of. So you have a certain concentration in the water, 0.015% concentration. Tritium is, of course, not available because that's an unstable nucleus and has a half-lifetime of 15-point-something years, something like that. And so there's no tritium in tritium depository available, or so a tritium mine or something like that. And so you must create that in situ by collisions of neutrons with lithium. And so you must invest some lithium in order to create the tritium. So it's an indirect way to create the fuel you need. Again, you can cast that in very simple figures. Just take the deuterium that is contained in a half tub of water here, and the lithium in the just standard accumulator. And if you then calculate the energy you get out of that, according to this ratio here, then you get 200,000 kilowatts hours electric, with all the efficiencies input in there. And that's enough to supply an average European for about 30 years. And so that's nice, actually, because you could say, I mean, it's a little bit propaganda, but you could say that everybody should have a half tub of water and an old accumulator, and then you're done. And so it's a big, big promise. It's a bit more complicated. If you go into the details, we can discuss that if you wish. Plasma confinement. I mean, the plasma must be confined, otherwise the plasma just disappears in space. So it's just a gas. It's an ionized gas, and the gas just vanishes if you don't do anything. But since it's ionized, it's electrically charged. The sun is just doing the confinement by the gravitation, as already mentioned. And so that's just the inwards directed gravitation that counterbalances the plasma pressure, just the gas pressure, which is outwards directed. We cannot do that on Earth, of course, so because of lack of gravitation in such a small mass we would like to have. In particular, we are talking about a low-density fusion plasma. And there, the recipe is to use strong magnetic fields. And here it is indicated the magnetic field is pointing inwards in the projection plane. Charged particles react by a gyro motion. That means all particles gyrate around the magnetic field. And the magnetic field is efficiently acting as an inwards directed pressure because particles cannot escape anymore from the magnetic field lines. And so it is efficiently a pressure, and this is expressed by this quantity beta, which is very much beloved by us plasma physicists. That's the ratio between the kinetic energy and the so-called magnetic energy, the magnetic pressure. The kinetic pressure over the kinetic pressure over the magnetic pressure. And here the magnetic pressure just goes as b squared, and so we need strong magnetic fields to counterbalance the pressure of the plasma. And this is shown how it is done. So after a long, long story, it turns out that the right magnetic field geometry, we have to talk a lot about the geometry, is the torus geometry. So you bend magnetic field lines to a ring, and in this way you avoid that magnetic field lines touch the wall because particles are attached to the magnetic field, and if the magnetic field lines touch the wall, the particles touch the wall. You must avoid that. And so you first form a ring. Great, so that seems to be the way to go. And you can create such a ring-shaped magnetic field, which is indicated here in green, just by magnetic field coils, which are indicated here in blue. And so that seems like the story is done. However, then a lot of physics happens. So if you have curved magnetic fields, the magnetic field is getting inhomogeneous, and you must do something because curved inhomogeneous magnetic fields cause outwards directed drifts. And basically, you have to deal with the situation you have if you want to get honey out of the honey pot. So the honey is floating down, and only if you turn the spoon, so we see these nicely specialized honey spoons, then you can keep the honey on the spoon. And you are doing a similar thing with your magnetic field lines. The magnetic field lines must be twisted, and not only bent to a ring, but in addition they must be twisted. This twist is done in this configuration, which is called tokamak. That's a Russian invention, and it's a Russian acronym, by the way. You do this by inducing a current via an additional solenoid here in the center. You are inducing a strong current in the plasma. This current is creating an additional magnetic field component. This additional magnetic field component combined with the magnetic field you are creating by the coil makes you the twist. Okay. Sounds great, and it's a great way to do it. And we have a fantastic tokamak in Garching in our institute in Garching that is performing in a world-class way. I'm going to talk more about another approach. That's the Stellarator. Again, you have a ring. Again, you need a twist. And again, to make the story very short, you make the twist by adding an additional set of coils and by running a current through this additional set of coils. And these are counter-directed currents, and basically you're creating an octopole field, a quadrupole field, sorry, so that is superimposed on this ring-shaped magnetic field. And if you superimpose these two fields, then again you get the twist. So that's the Stellarator idea, and that's also a pretty old idea from the 50s. But the Stellarators were actually not performing. So they performed much worse than tokamaks, and it was for decades. It was a big miracle. Why? And that after a long period of research, that turned out to be the way to go. And so this simple setup I've shown before, doesn't perform. This thing performs. It's the Wendelstein 7X magnetic field. How is it obtained? By numerics, by heavy supercomputing. And here in this symposium, there was already a lot of talking about supercomputing. Without supercomputers, Stellarators would not exist. And these were the early supercomputers anyway, but nevertheless, it's a very heavy numerics exercise. And here's just a list of codes which have to be tackled, and here that's just an eye catcher. So that's a code map. So these are coupled codes which deliver the data among each other. And if you do so, you can optimize. You can optimize along a set of criteria, and without going into the detail, just take note that there are 7 well-defined physics optimization criteria which must be satisfied in an optimum way. And so it's a typical optimization procedure. The outcome is then the shape of the magnetic field, which is indicated here by these surfaces, these flux surfaces, and then you can calculate the coils that belong to this magnetic field geometry. Just by inverting Maxwell's equation, and then you get the shape of the coils. And so the coils have the most natural shape, in a certain sense. That's what physics tells us is the magnetic field coil that belongs to this plasma. And then that's the basic of that establishes the foundation of Wendelstein 7X. Here we have the shape of the plasma and the shape of the magnetic field. That's the same thing. Created by the coils. by 50 coils in total, so shaped coils with a certain geometry. Then we have another set of coils, which is needed by our experimentalists to make some modifications, so to turn a few knobs. Then everything must be interconnected, so with pipes and connectors and bolted to a massive central ring. And the whole thing is getting technically difficult because it's a superconducting machine. And you need superconductivity because you would like to create a magnetic field for infinity. Yeah. So the magnetic field in which you create should act as a bottle. So as a bottle where you fill the plasma in and the plasma stays in there. And the bottle must just be there stationary. And then also the whole thing is stationary. So that's stationary confinement, and this is only possible by using superconductivity technologies, which also means that you have to deal with cryotechnologies, because that only happens at very low temperatures if you take conventional superconductors, at 3.4 Kelvin, to be more precise. Therefore, you need a cryostat. You need an outer vessel in which you create a vacuum, and so all the coils have to live in a vacuum. Of course, the plasma is living also in a kind of vacuum. First, you evacuate the plasma chamber, and then you fill something like 0.1 gram of plasma into that and create the plasma. And so it's very, very light. It's a low-density plasma. And that's how the machine in the end looks like, a little bit like a spaceship, I must admit. And that's the reality. That's our construction site. So during the machine construction, that was a long, long story, 10 years of construction, 1.1 million assembly hours. And this was an important moment. That was the insertion of the last module, the last fifth of the Wendelstein, into the gap here. And of course, many technicians and engineers are really busy in taking care that nothing is getting damaged during this insertion. Everything here in yellow are tools to lift this 130 tons heavy module. And the machine is complete. That's a view how the machine looks now nowadays. Right, and that's the first, one of the first plasma discharges we got. And that's how a plasma looks like. And it looks a bit boring, but it should look boring. So the ideal plasma is just a halo here, so a halo around and nothing in the center. So no light emission in the center because it's a hydrogen plasma. The atoms are not able to emit any light except for X-ray. But you see, if you inspect this, should repeat. Okay, but you have seen that also light emission starts to evolve at the edge and then penetrates in, and that's the story about impurities, because impurities are created by scratching just a few atoms from the wall, and these atoms make their way into the plasma, and then they emit a lot of line radiation. And so impurities must be avoided. That's, of course, all embedded in a very international endeavor, so we are by nature very internationalized. And these are the parameters so we achieved with Wendelstein already in the very first days, so sort of first weeks, 100 million degrees of temperature for the electrons, 20 million degrees for the hydrogen, and later already at pulse length at 1 to 7 seconds. And okay, this lady helped us a little bit, so when we started then the first hydrogen plasmas, so that was of course a big event after this long construction time, and it's a major, worldwide a major research facility. Right, just a few words on the impurities. So you do a spectroscopy, so high-resolution spectroscopy, so these spectra look like this, and so you, by means of the spectroscopy, you can identify what kind of impurities you get. And what is dominating is carbon and oxygen that comes from the wall. And in the beginning, so the concentration is relatively low. So here we have the axis, and in the end, after operating the plasma for a while, then you get much, much higher carbon and oxygen lines. And then you have to take care how to deal with these impurities. And of course, first you have to observe them carefully, and this is done by high-resolution spectroscopy, as shown here. And that's a typical shot plot, so how we plasma physicists do it. So here, that's the injected energy, 4 megawatt, 1 megawatt, and then we switch it on. Here is the time axis, 7 seconds, 1 second, and then you get all the other quantities, the temperature, which is between 10 keV and 5 keV, the density is observed, and what you see in here, there is just that everything is very nicely controlled and stable, and so it's a very tame machine. It does exactly what you want, and so it really behaves, the Wendelstein 7X. That was a very nice experience. Many things have to be extended, so we need better wall structures, so that's work that is currently ongoing in Greifswald, and so we are in the machine and doing assembly works. There's one of our worker behind this machine that is lifting up heavy graphite components to the wall. We need a lot of water cooling. more heating power in close collaboration with the KIT, more scientific instruments in very close collaboration with the Research Center Jülich. The power station then looks like this. So, I mean, things must get bigger. Here is a car. Here are the parameters, 1,400 cubic meter plasma volume you need. And so a power station would be a big beast. So it's a 1.5 gigawatt power station here. But the concept of the Wendelstein would say no current disruptions. That means no instabilities that lead to a disruption of the current that would exist in the tokamak. It is steady-state capable, but you have to do three-dimensional engineering, massively three-dimensional engineering. And that's, you can't call that complicated. It's three-dimensional. You must get used to the three-dimension. So I come to the summary. Wendelstein 7X. Here's a view of the machine and our control room. 15 years of construction with the design at the technical limits, certainly. First operation has exceeded all our expectations. It is a key device for the optimized Stellarator concept on the world, and still basic research, but I think with a great potential for the future. Thank you very much.